So next up, we have Jake. Jake Chuharski. And if you can just go ahead and take it away, Jake.
Oh, there we go. Can you hear me?
Yeah, we can hear you.
Right, cool. Let me share my screen. All right. Cool. Welcome, everyone. Thank you for coming. My name is Jake Chuharski. I'm an undergrad student at Massachusetts Institute of Technology at MIT. I'm studying math, music, computation, and cognition. And today I'll be talking about one approach to making music with adiabatic quantum computing and using some of the similar music theory from the previous talk. I'll start by giving a quick background into adiabatic quantum computing and then discuss the programming algorithms, a first-of-a-kind music generation program that uses the D-wave quantum annealers. And hopefully we'll have time for a demo and some quick questions at the end. All right, so as a little background, adiabatic quantum computation gets its name from the adiabatic theorem, which was originally stated as follows. A physical system remains in its instantaneous eigenstate if a given perturbation is acting on it slowly enough, and if there's a gap between the eigenvalue and the rest of the Hamiltonian spectrum. So let's examine this statement because it's not very straightforward. Put simply, if a given quantum mechanical system is subjected to gradually changing conditions, a slow perturbation, then the system will adapt its configuration and its probability density will be modified by the process. However, when subjected to rapidly varying conditions, there is insufficient time for the functional form to adapt. So the spatial probability density will remain unchanged. This also means that if the system starts in an eigenstate of a determined initial Hamiltonian, it will end in the corresponding eigenstate of the final Hamiltonian. And that's still pretty complicated. So before we go further, let's take a quick refresh on our eigenstates, Hamiltonians, and simple harmonic oscillators. So eigenstates can be understood from the example of a wave or guitar string, and it has its origins in German. The prefix eigen means own or oneself. So the eigenstate is a fixed value of its own state. When thinking of a guitar string, for an example, the string gives a sound and the eigenstates correspond with the rather stable ways that the string oscillates with the wavelengths that are integer fractions of the distance between the two connection points of the string, the overtone series. So those are your notes when you're playing the guitar. And as a fun aside, the reason it's called the harmonic series is, harmonies comes from music. So let's also refresh our understanding of Hamiltonian. In quantum mechanics, the system's Hamiltonian is an operator that represents the entire energy of the system. It corresponds to the sum of the kinetic energy plus the potential energy for the system. So Hamiltonians function as operators acting on the system, and we can develop other operators using basic ones. As some examples, let's consider the simple non-relativistic case and a case from quantum mechanics. In both of these cases, the equations represent the total energy of the system. So depending on what you're defining, you can have a different Hamiltonian spectrum. And let's also finally look at a simple harmonic oscillator. In physics, a simple harmonic oscillator is something that has a characteristic repetitive movement through a central equilibrium position, so that the maximum displacement on one side of this position is equal to the maximum displacement on the other side. The interval of time for each complete cycle is constant and does not depend on the maximum displacement. The cycle having constant time makes these oscillators great timekeeping tools. A mechanical metronome is a great example. So back to our definition of the adiabatic theorem, we can examine this through another example of a simple harmonic oscillator. Think of a pendulum hanging from the ceiling. A metronome is also a pendulum. Imagine our ceiling pendulum has a small balled weight at the bottom, kind of like this little rope and string I have here. If you start the pendulum at rest and don't touch it, nothing changes, which isn't very interesting. However, if you were to slowly pull the pendulum back, upwards, and release, it'll have a nice smooth arc through the air. And this smooth string is a good analog for our adiabatic motion. The pendulum will eventually settle again and do so pretty gently and predictably. Instead, if I was to, start jostling this pendulum around and throw it horizontally and smack it, you'll end up with a lot of jerky motion. That's much harder to predict. So the pendulum has experienced way too rapid of a change in its condition, and as a result, it's no longer possible to determine the path of the pendulum from the starting position, which is basically consistent with the definition above. All right, so let's look at our strategy for solving our adiabatic system. We first start by designing a Hamiltonian with the ground state that includes the solution for your optimization problem, then preparing the second ground state of a second simple Hamiltonian, and finally interpolating between them. If we change time sufficiently slowly by adiabatic evolution, and we start in the ground state of our second simple Hamiltonian, then we'll end up in the ground state of our goal Hamiltonian. And that's kind of how we solve our optimization problem through this adiabatic theorem. And here, that adiabatic transition ensures that we'll stay in the lowest energy solution throughout the change, which is exactly what we're looking for. Now, at this point, you might be wondering how slow is sufficiently slow. And, if you read the paper, there's more information on all these topics. But basically, because of the dependence of the runtime on the gap, the performance of the, there's a dependence on the runtime between the ground state and the minimum gap to the next the next higher state, eigenvalue state. And because of this independence on the runtime of the gap, the performance of the adiabatic quantum algorithms is strongly influenced by the type of quantum phase transition that the system would undergo in the thermodynamic form. So every time step in our transition will have a different gap, and our speed limit, what the maximum speed you can go without breaking these adiabatic transition limits, will be dependent on the inverse of that minimum gap squared. So 1 over delta squared. So in the instances where the minimum gap is very small, our speed limit can scale exponentially for select MP hard problems. And we end up with nearly infinitely long runtimes for such problems. So adiabatic quantum computing is somewhat idealized in an attempt to solve problems because the minimum gap is often hard to calculate. A less idealized version of the adiabatic quantum computation is known as quantum annealing, which is what the previous presentation was talking about. And quantum annealing is a method to solve problems requiring the system to run repeatedly, likely breaking these adiabatic conditions, which gives you thousands of different configurations with different energy levels. And you can pick the one with the lowest energy by using probabilistic sampling. So there's no guarantee that this ground state or global optimum for the problem, but this problem may still yield a better solution than a classical algorithm. And it's also worth mentioning that adiabatic quantum computation assumes a closed system, although in real life, quantum computers end up being coupled to the environment through a thermal bath at a low temperature. The thermal bath helps to facilitate energy exchange from the processor and the environment, but cannot fully isolate the system. Fortunately, the speed limit and thermal exchange shouldn't matter too much while making music. All right, so the program algorithms will be our example of quantum music, which is made using D-Wave quantum computers. Their most recent architecture is called D-Wave Advantage, which has over 5,000 qubits on the QPU. So as a little more background, D-Wave also supports a Python-based open source SDK, Ocean, a package for development of apps that use their quantum computers. Advantage and Ocean are both accessible via their Leap solver. It's an online version, and we'll take a look at that today. D-Wave's real-time quantum cloud service. So algorithms uses both the D-Wave local annealing simulator and the D-Wave Leap hybrid solvers. The D-Wave quantum annealing processors naturally return low energy solutions. Some applications require the real minimum energy optimization problems, and others require good low energy samples, which are probabilistic sampling problems. The system begins by placing qubits in an absolute minimum. The hardware then slowly alters the system configuration using magnets so that the energy landscape represents the problem to be solved. The qubits will return the lowest energy state of the landscape, which in their final state will represent a solution to that problem. The landscape can further be shifted around to represent a problem structured as a minimization of Hamiltonian energy. The landscape should look kind of like the peaks and valleys, and there's a chance that the system will get stuck in a valley that's not necessarily a global minimum, although the system should be able to take advantage of quantum tunneling to move out of these valleys. The process isn't deterministic and can sometimes stay stuck. However, getting stuck doesn't always matter because in many cases, a solution that is near the absolute minimum can be worth as much as a true global minimum. And in situations where it matters, the problems can be run many times and the solutions can be identified by frequency. The computers can also run a method called reverse annealing, which has the qubits start at a known minimum, and then the qubits are released in the hope that the qubit will tunnel to a better solution. Algorithms has a built-in command line interface that allows the user to choose between the local quantum simulation solver or an actual quantum computer at D-Wave, accessible via their Leap cloud service. The interface also allows the user to pick a name, duration, and happy versus sad. So we chose to set up our music as a probabilistic sampling problem. So if we set up the problem using a Bayesian network, then we end up with chords or notes defined as nodes connected by probability chains that determine the switch between them. Similarly, a Markov chain is a graph that's used to represent state machines. It consists of nodes representing states and edges representing the transitions between those states. The edges can be weighted and oftentimes represent the conditional probabilities of transitioning from one state to the next. Markov chains are very relevant to music generation because we can encode the desired notes as chords, as states, and using some basic music theory, define edges and transition probabilities between chords that should be played in succession. Now, how can we generate music with this Markov chain? It's simple. We can perform a random walk on the matrix. We start at a given state, and using the transition probabilities, we can determine which state to go to next. This process has no memory, only the current state is ever taken into consideration. In order to implement a random walk or Markov chain Monte Carlo simulation using D-Wave samplers, we have to change our setup just a little bit in order to formulate it as an optimization problem. This can be done using Markov random fields, which define relationships between and dependencies between vertices instead of transition probabilities. Converting from a normal Bayesian network, a Markov network with conditional transition probabilities, into a Markov random field is a process called moralization. So each edge, A, B, can be a 0, 0, a 0, 1, a 1, 0, or 1, 1, indicating the binary values of its vertices. Each of these states is associated with a potential energy, and our objective now is to find the lowest energy state of the entire Markov network. So we'll consider the one state as a chord being played. This is some of the sample code of how we set up our nodes. The 0, 0 and the 1, 1 edges were assigned to be arbitrarily high potentials to avoid states where the current note is being played again, or two notes are being played simultaneously. This is done for each chord and note sequence. We then encode the chords into a MIDI file, which is returned to the user and can be opened in software such as MuseScore to play back and see the score. Luckily, D-Wave has a Python language package for exploration and analysis of network and network algorithms called D-Wave Network X. This allowed us to create simple Markov random field for chords 1, 2, 3, 4, 5, 6, and diminished 7 in the diatonic chord series. Defining the potentials with D-Wave Network X is easy. The desired states are assigned lower potentials. In this example, the lowest energy state assigns 0 to each node in the network. All right, so I'll go through a quick demo to see the program in action. While staring at pictures and listening to me explain what it does and how it works is great, but if I can show you exactly how it works and what it does, then maybe we'll get a little bit better of understanding. So hope you can all still see my screen. Can everyone see the command line? Great. All right, so let's run it. So this is algorithms. This is our little command line interface. We can call our song whatever we want. I'll call it Symposium. And we can choose the song duration in seconds. If I'll start by making it, maybe a 30-second song. And we can use a local versus leap solver. So the local versus leap solver, basically D-Wave gives a package that allows you to simulate a quantum environment on classical computers. And so that's kind of what the local solver is. And the leap solver actually sends the data to D-Wave in Canada and uses their solvers as queues up their solvers. And they actually give out minutes to developers to use on their quantum computers. So that's what I'm using here. And for the hackathon that we participated in, they gave us a bunch of time for that. So anyone can use this program on both the local and leap solvers. The leap takes a little bit more setting up, but it's definitely doable. So I'll start by doing it on the local solver just to save some time. And we have a happy versus sad song. So the happy songs use the major diatonic chords, 1, minor 2, minor 3, major 4, major 5, minor 6, and diminished 7. And then uses the random walk over a major pentatonic to try and get kind of a solo-y feel and without having to rely on too much very strict music theory, get a good kind of approximation of something that should sound okay. And when you run it, we'll end up with our song right here. And I can go to MuseScore and open it. It's called Symposium. And here's our little song. Hopefully I'm showing audio. Let's double check. Yes. All right. Let's see. Let's give it a listen. All right, so that was our happy song. We have it at about 100 beats per minute, and as I was saying, we use the diatonic chords and a major pentatonic to achieve this sound. It's not perfect, and it doesn't follow all the rules of counterpoint. Although it's easy to add any of the music theory that you need in these transition probabilities in order to attain some of these different. A counterpoint or a jazz, or you can change the chords however you want in order to get a different genre of sound. Also, if you're listening carefully, I'm not sure how many people are paying attention to it, but there's also dynamics encoded. So you can go from there's a 1 to 128 bit range for encoding dynamics in the Python package Mingus that we chose. And some of the notes are played harder than others, so you get some note velocities when using the MIDI. All right, and then I'll just run it again, and I'll just leave it here, and we'll do a, let's see, we'll do like a 10-second song because the leap solver takes a little bit longer because you have to use the internet. And I can do a sad song this time. And so this will send it to the sampler, and it can take a second. Maybe I should have set this one running first, and then we could have done the other one. Oh, there we go. All right, I must have good Wi-Fi today. Let's see. No, I do not have it. It says 100%, but oh, there we go. Okay. My first quantum song. All right, a little shorter, but this one is our sad song, so 60 beats per minute. It uses minor chords and a minor pentatonic. There we go. So that was a little bit shorter. I generally try not to, when I'm giving a demo, use longer songs for the leap annealer because there's often queue times for how long it takes to wait. So for the interest of time, I'm not going to do that. But if you want to download it and try it yourself, it's on GitHub. It's pretty simple, straightforward to set up. I can do another example of a quantum song. We'll make it a little bit longer, and we can do the sad one again if you guys want to hear that. Let's see. Here we go. This was a little bit longer. So it just gives a little bit more of a minor vibe when listening to the song. Yeah, so this is basically our program algorithms. Uses the Python package Mingus to create music, although I don't recommend it. I recommend using Music 21, which is what the last group used. And if I was to do it again, I would use Music 21. That's a program that one of my advisors here actually has been working on, and I've spent some time looking through the documentation. And it's much better than what we're using. But if anyone's interested in using it, I definitely recommend downloading it. And let me go back to my slide here. So as some final remarks, Adiabatic quantum computing is a great way to generate music using quantum computers, although at the time of this presentation, adiabatic quantum computing gives no real advantage to creating algorithmic music over classical computers in terms of an optimization standpoint. The exploration with algorithms has allowed for music to be successfully generated on real quantum computers. So currently, the actual quantum hardware provides a reduced speed in comparison to using the computer simulated environment, which is due to these queue times and the annealers and internet speed. So that's why, that's part of why I had to give a shorter demonstration. But of course, this may change as hardware continues to become increasingly advanced. And if I had direct access to the LEAP annealers, you could make a pretty long song pretty quickly. There also seems to be an inherent order in the world of science and math and music and all this beauty and elegance of the sciences. It's really hard to believe that there isn't a next frontier to music that we're yet to open the door into. I think this symposium on quantum music really might be the next frontier of music creation. So the program algorithms and all of these other papers that we've been talking about provides proof of concept that music can be created on quantum computers and can be expanded to create music of almost any variety. I'm very confident that there are abundance of applications for this software and this hardware, and it may become a vital part of the music industry one day. And D-Wave presents ample opportunity to experiment and play with the actual quantum hardware through their LEAP and Ocean. So if you guys want to download algorithms, give it a try. I have the GitHub here, and yeah, thank you. Open the floor for some questions.
All right. Thank you so much, Jake. Okay, so we have one question here that says, if you go for the local solver, how many qubits do you simulate with that compared to the 5K at the LEAP QUP?
Yeah, so I actually am not sure. When they released this solver, they weren't using the Advantage QPU. That is much more recent than the implementation of the solver. The last one they were using had 2000 qubits on their QPU. So I'm assuming it's probably simulating around there, although I'm sure if they haven't already updated it, there is likely going to be an update that simulates a similar number of qubits.
Okay. And then, and do you notice a difference between the physical annealing and the simulated one? And have you ever tried Fuji's Stewie, I think?
I'm not sure what Fuji Stewie is. I should probably look into that. The Fujitsu annealer. No, I haven't tried that. Although I should definitely look into that. I'll write that down. When I've used the physical annealing and the simulated ones, I haven't really been able to see that much of a difference, just because of how the chords are generated. But other than the run times, it seems to be pretty similar in what's output, and it outputs something different every time. So it's hard to really get a one-to-one comparison if you're trying to compare two different pieces of music.
Right, thanks. And do you see any differences in applications for music applications for quantum annealing versus like superconducting qubits or any other kind of photonics what we saw this morning?
Yeah, that photonics thing's cool.
Yeah.
I'm not sure. I mean, I'm sure there's when we were listening to the photonics and the the kind of synthesizers earlier, that gives a very different sound, and that's not using a direct MIDI output in that case, I don't think. So this is heavily leveraging on classical computers by using the MIDI interface, and it's kind of more of a hybrid solver, a hybrid program because it's I'm using MuseScore to listen to it, and you can use anything on a classical computer to listen to it, but you're not actually going to be listening to these on a quantum computer for what we have right now, and maybe there will be a way to do that, but that's not something I know of. So yeah, there's definitely differences in all of these different things and how you're doing them, and I think there's a wide variety in the different things that you can do with all of these different applications.
All right, thanks. And does anybody else have any more questions or comments? Everyone's saying it's a fantastic work, and thank you so much. Yeah.
Thanks for coming, everyone.
Yeah. Well, I think that is it for this paper session. Thank you, everybody. I think this was the last paper session.